Okay, in junior science you would have looked at the idea that all things are made up of atoms. So if you look at gold, you've got gold atoms inside of a certain size and behaviour. If it's an element, the atoms inside are all identical. So if you look at the first element here on the table, hydrogen, hydrogen's actually got all identical atoms, and then they're the smallest ones, the ones with the least mass. And as you go along the table to helium and lithium and beryllium and so on, you're increasing the atomic number that they've got on these tables. And they're actually getting more massive or heavier, if you like, each atom is. So they go up in, you can think of it as going up in size, I suppose, but that's not strictly correct. But in terms of mass, they're definitely increasing as you go along this table. Okay? And the atomic number tells you the order on the table there. But it's got some other meanings we're going to look at in a minute. The idea of the atom was it was an indivisible particle because it came from the word atomos, which meant indivisible in Greek. So what we're going to have to do here is look at how did that change over a century ago. So what actually was discovered was the electron by J.J. Thomson. So that was the first evidence of a subatomic particle, something that was smaller than this indivisible particle of any substance that we thought of. So we're going to focus on the nucleus in this section rather than the whole atom, including the electron structure. We're just focusing on the central part. So how did this come about? The discovery of the electron by Thomson meant we had to come up with a model of the atom that was actually including the electron. Now the electron was very tiny, it was negative, and we had to include that within the atom. So Thomson came up with a model that was actually subatomic, and he said, okay, let's say we had something here that had 2, 4, say 6, 7. The seventh element on the periodic table would have 7 negative charges and a charge of 7 plus, so that it was neutral. So he came up with the idea of a plum pudding model. It was basically a pudding which contained like a positive dough, I suppose, or positive jelly if you want to think of it that way, and negative raisins inside that. And the electrons would have been arranged to keep this balance between the positive charges and the negative charges. So we have a model for each of those elements showing them how they could be placed, those raisins or those negative electrons, to keep it balanced. So that was the first thing. Now this model stood for a little while until a new experiment was done. Now, Rutherford had some people working for him called Geiger and Marsden who did an alpha particle scattering experiment. Now what they did with those is they actually shot positive particles, these alpha particles, at a thin layer of gold foil, just there, okay? And when they did that, they expected all the particles to go straight through here based on the fact the positive particles would be attracted to the negative raisins there, but they would also be equally repelled by the positive dough. So they didn't think they would get much deflection, they come straight through. That was what they presumed. When they came to do it though, they found out that they actually were deflected by large amounts up to 180 degrees. Okay? And they had that as a detector around here to show that. So that was a very big surprise. Now the only reason positive particles would be deflected as much as that is if they were slowed down and stopped and repelled backwards. So what would repel a positive charged particle? Positive ones. So because it was such a large deflection, they assumed you had a very big concentration of positive charge somewhere. Okay, and Rutherford came up with this model here that the central nucleus here, if you like the sun, would contain all the positive charged particles. Okay, and the electrons would orbit around that as negative charges, just like the planets do. And the force of attraction wouldn't be gravity, it would be the electrostatic attraction between the positive and the negative charges. Okay, so that was the Rutherford model. They also found that virtually everything did go straight through, and therefore it had to be mostly empty space, the atom. So these electron charges had to be a long way away, and the nucleus had to be very tiny. So they were able to predict the size of the nucleus and the rough size of the atom based on the percentages of their deflections. Okay, so that was a key experiment there. So what you can see there is the notes on that. Okay. Now that kind of changes our whole understanding of what's going on with the inside the atom here. This periodic table then, when you look at it, H1, hydrogen 1, the atomic number of 1 here, that atomic number 1 actually now tells us the number of pluses inside, the protons. They call these protons these positive particles that they propose would be inside the nucleus. And it also tells you the number of electrons going on the outside of that. They're tiny, the electrons. So the electron is very small. So tiny electrons. So H1 would have 1 proton and 1 electron inside it. Okay? Whereas helium, here, He2, has an atomic number of 2, it's the second element. It would have 2 electrons and 2 protons. And so on down the table as you go through. So that was a key thing. We actually now knew so many protons in the nucleus in the centre, so many electrons on the outside. The other thing to bear in mind though was, if you actually look at some of these, so you look at say magnesium 12, that would have had 12 protons inside a central nucleus that was tiny. Now the problem with that is, of course, if you've got so many protons inside this nucleus, then you've got a huge amount of force pushing these away. So the nucleus should actually fly apart, especially when you consider that any one proton here is being pushed away by lots of protons here. This one's going to push it away, that one's going to push it away, this one's going to push it away. It's got a lot of force from all those protons being added together as a vector sum, pushing it away. So when they did this, Rutherford proposed that there was a neutral particle inside that sort of acted more like a glue that held it together. So he called a neutral particle in there a neutron. So when you look at the atoms made up of protons, neutrons and electrons, and this will be the typical model you've been used to in junior science, okay? The mass number here then, the mass number here tells you the total number of nucleons or protons and neutrons inside the nucleus. So they're called nucleons because they actually reside inside the nucleus. So if you actually had a mass number here of say 2, it would mean, if you were drawing an element for this, we would draw it as 1 proton in the nucleus, okay? And we've got to get to a total of 2 nucleons there in the nucleus. So 2 take away 1 would tell us we need to add a neutron inside. So that's the nucleus for hydrogen 2,1. This has got a name called deuterium, by the way. It's not the normal hydrogen. So you could do that for all of these, by the way. As long as you know the atomic number and the mass number, you can work out the number of protons and the total number of nucleons altogether inside the central nucleus. Okay? So if we start to look at some of the other nuclei that could be around, if we take lithium 3,7 then, you've got an atomic number of 3. So we're going to be drawing 3 pluses in the nucleus. And to work out the number of neutrons, we would subtract those. 7 take away 3 equals 4. I need 4 neutrons inside. 4 neutrons in there. So that's your central nucleus there, made up of those. So have we got a total of 7 there nucleons? Yes, we have. 1, 2, 3, 4, 5, 6, 7. So we've got a number of nucleons correct and the number of protons. Don't forget there would also be 3 electrons on the outside here, balancing that out. 3 tiny, tiny electrons, much, much smaller than those 2 protons and neutrons. So they'd be orbiting at large distances at high speeds. Okay. You could try some other ones there. Carbon 6,4,12 is a typical carbon one. So that means you'd be drawing 6 protons inside the nucleus, and 12 take 6 neutrons. Okay, there's your nucleus there. And don't forget the 6 electrons as well. Now, interestingly enough, carbon 12,6 is not the only form of carbon. There are other forms that are radioactive, which we'll come back to later. But these here are called isotopes of the same element. Now these isotopes are the same element because they've still only got 6 protons. Every one of them has 6 protons inside, so it's still the same element. Still 6 electrons, still the same electron structure, and they're going to behave in chemical reactions identical to each other because they have the same structure. Okay? But there are heavier versions inside the nucleus there that contain more neutrons. So if you look at this, what we would have here is 6 protons to this one, okay? And this time 13 takes 6, 7 neutrons inside the nucleus. Whereas the next one is still carbon because it's still got 6 protons there, but now it's got 8 neutrons. Alright, so this is radioactive carbon there. Okay, but they're all isotopes of the same element. Same number of protons, okay, same atomic number, got different number of nucleons inside because of the change in mass there. We still have to solve the problem of, for the really large elements, there's so much electrostatic repulsion due to all those positive charges, why doesn't it fall apart? So we need to look at nuclear force next. Okay, thank you.